In this video, we're going to take a look at some different quality of service or QoS mechanisms. First, let's identify when or if we might need QoS. One time we might need QoS is in a situation like this where we have a speed mismatch. Notice that we're coming into router R1 on a gig link, but we're going out to the IP WAN on a fast Ethernet link. That's a 10-to-1 speed mismatch. And if traffic is coming in faster than we can send it out, that could cause some congestion on the output interface of that router. Or maybe we don't have a speed mismatch. Instead, we have an aggregation point. Here we've got an Ethernet switch and all the ports are running at a gig speed, but maybe we've got a bunch of servers coming into the switch and we're all trying to leave this server farm on a single gig link. We're coming in with multiple gig links and leaving on a single gig link. That could cause some oversubscription of the bandwidth and cause congestion even on a high-speed switch network. The great news is we've got some quality of service mechanisms that can help us out in situations like this. However, if we're congested all of the time, we need more bandwidth. Quality of service is good for periodic congestion. Maybe there are specific times of the day when we're congested. Maybe everybody is coming in at 8 a.m. and they're firing up their computers and they're synchronizing their Dropbox accounts and there's a lot of network traffic, or maybe overnight we're doing a network backup. That might cause some congestion. If we just have those periodic times of congestion, yeah, quality of service might help us out. But if we're congested all the time, we need more bandwidth. And quality of service breaks down into three different categories. We have a best effort category that's not strict at all. In fact, I even hesitate to call it a quality of service category because really it's FIFO. First in, first out. The first packet that comes into the router or switch is the first packet to go out. There's no reordering of packets. There's no prioritization. It's just first come, first serve. That's best effort quality of service. Another QoS category we have is diff serve. That's less strict than our most strict, which is the bottom we'll talk about in a moment. But diff serve is short for differentiated services. This is typically what we're going to be using in our enterprise networks. We're going to mark traffic with a diff serve marking. Specifically, it's a DSCP marking, a differentiated services code point marking that's going to identify the relative level of priority and drop probability for a packet. There is a more strict option for QoS, and that's called INT-serve, which is short for integrated services. The mechanism I want you to know here is RSVP. That's the Resource Reservation Protocol. And it can make a hard and fast reservation for an application. And it can say that during this application, nobody else is allowed to use this bandwidth. Even if this application doesn't need it at the moment, it's reserved. And until that application stops and gives that reserved bandwidth back to the bandwidth pool, nobody else can use it. That doesn't really share bandwidth. It doesn't make the most use of available bandwidth. So typically we go with the less strict option, or diff serve. Now let's take a look at some specific QoS mechanisms. And the first one is classification and marking. And Cisco says that we should classify and mark our traffic as close to the source as possible. As an example, let's say that I'm going to be traveling on an airplane. And currently, I've not earned silver medallion status or whatever they call it on Delta Airlines. I fly Delta a lot. But imagine the day comes. Imagine the day comes where I earn that frequent flyer status and I get to get on the plane first, and I go up to the gate agent and they say, "Hello, Mr. Wallace, before we let you on the plane, can you prove that you're a frequent flyer? Can you produce the boarding pass from the time you went to San Jose and to Orlando and to Austin and to Las Vegas?" No, that wouldn't be efficient, would it, if I had to prove myself every time I got on the plane? So what do? Well, they give me a marking on my boarding pass that says something like Sky Priority, and that tells them that I am a priority passenger. I get to get on first. It's the same thing with our network traffic. Very early on in a packet's travel, we're going to recognize it. We're going to classify it as being a particular type of traffic, and we're going to mark it. But classification and marking by itself doesn't really alter the behavior of packets. We need some other mechanism that's going to look at that marking and make a decision, like a forwarding decision or a dropping decision based on that marking. An example of a mechanism that can do that is queuing, which is also known as congestion management. You might see that in the literature. But queuing is going to influence how a router or a switch forwards packets out of an interface's output queue. Remember when we talked about the speed mismatch a moment ago, and we were coming into a router at a gig rate, and we're trying to leave it at 100 megabits per second? Well, what's going to happen to those packets that we cannot send right now? Well, that output interface can reserve some memory called a buffer or a queue, and it can store those packets that we just don't have bandwidth to send at the moment. It can store those packets temporarily in that queue. And then when bandwidth becomes available, we can take the packets out of the queue and send them on their way. Now, if we just did this on a first come, first served basis, that would be the not strict. That would be the best effort flavor of QoS. However, we might want to have a little bit more control over how packets get forwarded out of the queue. After all, that queue is of a finite size. It can only hold so many packets. Imagine that we had this big data burst on the network, and we're flooding traffic trying to go out to the IP WAN, and that queue is filling up, and eventually it's going to fill to capacity. It's going to start to overflow. We're going to be dropping packets, high priority packets, low priority packets. We're dropping everybody. But what if we did something very simple? Let's say that we took that output queue and we divided it into two queues, two sub-queues. Maybe we're going to put voice over IP traffic in one queue or one bucket, and we'll put everybody else in the best effort queue or the best effort bucket. Now, the best effort queue, it might fill up, it might overflow, but meanwhile, the voice over IP bucket is not overflowing. We're not dropping voice traffic because we've done this basic queue separation. Now, in the enterprise network, Cisco says that we should create no more than 11 of these sub-queues. After all, if everybody is special, then nobody is special. So what we're going to do is probably create several of these sub-queues, no more than 11, and we're going to put different categories of traffic into different queues to give us that queue separation. And we can give different bandwidth guarantees to these different queues. We can even say that a queue is a priority queue, and traffic in that queue gets to go first. That's a queuing technology called LLQ, or low latency queuing. However, if we don't give priority to a queue, but we just set a bandwidth guarantee for each of the queues, that's called class-based weighted fair queuing. Those are a couple of the queuing mechanisms I'd want you to know about. LLQ has a priority queue. Class-based weighted fair queuing does not have a priority queue. And while queuing can give us a minimum bandwidth reservation, congestion avoidance is going to give us a mechanism to prevent a queue from filling to capacity. Bad things can happen when a queue fills to capacity. Not only does it overflow and start to drop high priority packets, low priority packets, it also causes TCP flows to go into TCP slow start. Do you remember how TCP works with the sliding window? We set up a TCP session with the SYN-ACK, and the ACK, that three-way handshake, and then we start to grow that window size. I might send a TCP segment to the other side, and it says, okay, I got it. Send me the next segment. And I say, wow, that was successful. Instead of sending a single segment, I'll send two segments. And I get the acknowledgement for those two segments, and I say, well, let's double it again. Let's go to 4 segments, and then 8. 16, 32, 64, 128, 256, 512, 1024, 2048, 4096, 8192, 1634, 32768, and that's as high as I can go from memory. But we double until there's too much time that elapses before we get an acknowledgement, or we get an acknowledgement requesting a segment that we already sent. That's an indication that we're sending too aggressively, and if either of those two conditions happen, we go into TCP slow start, where that window size takes a precipitous drop. It drops and we start to send traffic at a much more conservative pace. We'll send a little bit and we'll wait for an acknowledgement. Send a little bit and wait for an acknowledgement. We're not using bandwidth as efficiently. And that's not a big deal for a single TCP flow, but think of this. If a queue fills to capacity and every single TCP flow simultaneously starts dropping packets, you guessed it, every single TCP flow is going to simultaneously go into TCP slow start. That's a condition sometimes called TCP synchronization or global synchronization. What it results in is an incredibly inefficient use of bandwidth because everybody is going into slow start at the same time. We can prevent that using congestion avoidance. And the congestion avoidance mechanism we typically use on Cisco routers is called weighted random early detection, or WRED, weighted red. And what it's going to do, it's going to set different thresholds for different packet markings. And it's going to say, as long as the queue depth hasn't exceeded this level, you're welcome to come in. But if we have exceeded a level for a particular marking, we introduce the possibility that we might occasionally throw some of those packets away. And the deeper the queue gets, the higher the probability that we're going to throw away a particular marking. And it's set up such that we'll never fill to capacity. And the reason I have the Vulcan live long and prosper symbol on the screen is congestion avoidance, or weighted red. It reminds me of my favorite Star Trek movie. It's Star Trek II, The Wrath of Khan. Back in the 80s, you might remember Ricardo Montalban played Khan. In that scene toward the end, the Enterprise is damaged. Khan is about to blow them up. So Spock, he goes down to fix the warp drive. And he goes into this room and he gets poisoned by the radiation in the room and he's blind. And Kirk comes down to see him, and Kirk goes up to the glass and he says, Spock! And Spock comes to the glass and he says, ship out of danger. And Kirk says, yes. And they go on to have this discussion. He says, why did you do it, Spock? Why did you give your life to save the Enterprise? And I paraphrase here. Spock said, don't grieve, Admiral. It's logical. The needs of the many outweigh the needs of the few. And then Kirk says, or the one. Well, that's what weighted red is doing. It realizes that the needs of the many TCP flows outweigh the needs of the one TCP flow. And it will throw away packets from individual flows. It'll make those flows suffer so that everybody doesn't have to suffer. That's what weighted red does for us. Our next QoS mechanism is policing and shaping. Now together, these are called traffic conditioners. And they will set a speed limit on our traffic. Unlike queuing, which gave us a minimum bandwidth guarantee, policing and shaping give us a maximum bandwidth limit. And policing is a bit more harsh than shaping. If we try to go above a speed limit called the CIR, the committed information rate, with shaping says, I'm so sorry, I don't have enough bandwidth to send you at the moment, but don't go anywhere. Let me temporarily put you in this queue, and then when the bandwidth demand dies down, I'll take you out of the queue and I'll send you on your way. So shaping is delaying traffic when it tries to exceed the speed limit. Policing by default is much more harsh. It is going to, by default, drop any packets trying to exceed that speed limit, that CIR that we've set. And the reason I have a bowl of soup on the screen is it reminds me of that Seinfeld episode where if you don't order soup correctly, the guy says, no soup for you, come back 1 week. That's what policing does. It says, no bandwidth for you, come back. Literally come back, because we're causing TCP segments to be retransmitted. So policing and shaping, or traffic conditioners, they're setting speed limits on our traffic so we don't have a particular traffic type consuming too much bandwidth. And the final category is link efficiency, and this, as the name suggests, is trying to make the most efficient use out of a relatively limited amount of bandwidth. Now, to be honest, this is not nearly as important as it was a few years ago, because now our link speeds are typically higher. We've got gig links all over the place these days. But if you do have some slow link speeds you're dealing with, then you might want to consider a link efficiency mechanism. And what do I mean by low speed? Well, first of all, take RTP header compression. That's one of the link efficiency mechanisms. RTP, that's the real-time transport protocol. That's what we use to send voice traffic and also video traffic. And if you look at the header of a voice packet, it could be 40 bytes in size. If we use a coder-decoder or a codec of G.729, that's a common codec for voice that's going to save bandwidth. If you look at the header and you add up the IP header and the UDP header and the RTP header, it's a whopping 40 bytes in size compared to a payload size of only 20 bytes. That's right, the header's twice the size of the payload. That's not a good ratio. So what RTP header compression will do is it will make this observation. It will say, you know, as we send packets as part of this voice conversation between these two routers, each of the headers have a whole lot in common. All of these headers in this flow have the same source and destination IP addresses. They all have the same source and destination UDP port numbers. They all have the same RTP payload type. Instead of sending all that redundant information, what they do instead is cache it. They make a copy of it and they put it in memory in the routers at each end of the link, and they just don't send that information. We'll strip off that 40-byte header on one router, send it over the relatively low-speed WAN link, and when it gets to the router on the other side, we put it back on because we've made a copy of it. Now, we do have about 2 bytes of header that identifies what voice conversation this is a part of. We don't want to get confused. That's going to be 2 bytes in size, or we could use a UDP checksum and that would make it 4 bytes in size. But typically when we do RTP header compression, we're going to have a 2-byte header instead of a 40-byte header. By the way, Cisco says that this is appropriate when the link speed is less than 2 megabits per second. So fairly slow WAN link speed, less than 2 megabits per second. The other link efficiency tool I want you to know about is called link fragmentation and interleaving, or LFI. That's the reason I've got the tractor trailer on screen. Now, this tractor trailer looks like it might have a couple of trailers behind it, but there are some tractor trailers out there that have 3 trailers behind the tractor in front. And imagine that you're in your little tiny sports car and you're behind one of these big triple tractor trailers and you're at a traffic light. And the light turns green, and slowly the tractor trailers start to go through the intersection. The first trailer goes through, and the second, and then finally the third. By the time you get to the intersection, the light's probably red again. That's a lot like our voice traffic getting trapped behind a big data packet. For example, if we had a 1500 byte data packet trying to go out of an interface, just to give you an extreme example, if we had a really slow WAN link, let's say 56 kilobits per second, just because of easy math, it would take 214 milliseconds just for that data packet to get out of the interface. And that would adversely delay the voice traffic, and it would give us poor voice quality because we've got too much delay. What we could do instead is take that big data packet and break it up. Going back to our tractor-trailer metaphor, instead of having one tractor with 3 trailers behind it, what if we put a tractor in front of each of the trailers? Now we've got 3 separate vehicles on the road. We've got 3 separate tractor-trailer combinations. And in our little tiny sports car, we're nimble, we're agile. We could probably weave in and out and get ahead of 1 or 2 of those tractor-trailers. That's what we can do with link fragmentation and interleaving. We can take that big data packet and bust it up into little tiny fragments. And then, just like we're shuffling a deck of cards, we could shuffle in the little tiny voice packets in amongst the now fragmented data packets. And as a result, our voice packets get through the interface sooner. Now, where does Cisco say that we should use link fragmentation and interleaving? It's when we have voice or video traffic on a link speed of 768K or less. That's pretty slow. You probably aren't going to run into too many of those. But if you do, and if you're running voice or video, it might benefit you to consider using link fragmentation and interleaving. If you use link fragmentation and interleaving on higher speeds, it starts to hurt you more than help you. Because if you think about it, when we fragmented that big data packet, we had to put a header on each of those fragments. We now have more headers than we did before. We're actually using more bandwidth than we did before. But it's a valuable trade-off if we're on a lower link speed and we can get voice packets ahead of some of the traffic, but it starts to hurt us more than help us if we're above 768 kilobits per second. And that's a look at some of the common quality of service mechanisms we have.